Guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this specific discussion, I'm basically going to look at a few concepts which are going to assist us in interpreting the concept of De theorem. This particular theorem is concerned with finding the roots and, of course, the powers of complex numbers. Now, in this case, we're going to look at set square angles and the periodicity of the sine and the cosine function. Now, we have come across this specific concept of periodicity and the sine and the cosine function from a previous discussion on the concept of waves and other areas of AC currents, oscillations, and other different kinds of oscillations which entail the aspect of waves. Now, in this case, we are going to look at that specific characteristics, which is going to be, or the specific characteristics which are going to be assisting us try to interpret this specific aspect of De Moivre's theorem. Now, in a sense, if we can look at this specific aspect of the concept of the sine and the cosine waves, or the cosine functions, we can have these two particularly graphs which are going to be demonstrating these specific, of course, functions for the sine and the cosine. So I'm going to have this one given as that range of value for the amplitude together with a change in x, which is going to be given in terms of theta. So in a sense, I'm going to be having those two specific graphs given as such. So we shall have this particular function which is going to be given for the sine function given as sine over theta, and then I will have the lower section giving us a function of the graph of this specific function for the cosine over theta given as such. So in a sense, I've just mentioned this specific term of periodicity. Now, periodicity is basically going to be referring to the repetitive nature of this specific wave at an interval of 360 degrees. Now, in this specific case, we are going to see that, therefore, we are going to have this particular cycle for the sine, of course, a function given from this specific range of 0, which is going to be forming our reference. And then we shall have this specific complete cycle going for this particular case at 360 degrees. So for the cosine function, this is going to be starting at the origin at this specific point, and it's going to be having this complete cycle at this specific point, which we will have in terms of 360 degrees. This is a particular peak which I've just chosen for the amplitude given as such. So we can analyze these specific graphs perhaps for the various points which we are going to have for this particular cycle. And this one we're going to have 180 degrees situated at that specific point. So the other range of divisions are going to include 90 degrees, perhaps 270, and the rest. And in this case, what I wanted us to particularly note from this specific case, the concept of the sine and the cosine functions are going to be forming this aspect of periodicity, whereby we're going to see that this basically is going to be finding wide application in the previous areas which are mentioned in my previous statement. Now we're going to see that n angle which we are going to define in terms of theta, that's going to be differing by a multiple of this 360 degrees. They are going to be having the same function which we are going to have in terms of these two trigonometric ratios of the sine and the cosine function given as such. So in a sense, we are going to see a connection between the two. That n angle that we can define by this is going to be, of course, having a multiple that is going to differ by a multiple of 360 degrees is going to be having the same trigonometric function for the sine and the cosine of this particular function. And therefore, this is going to be, of course, referred to as periodic functions, which are going to be obeying that specific law. Now, if we try to consider these specific triangles which I've just given on the right side of the board, I'm going to look at them, of course, and let's try to figure out some of the, of course, angles which are going to be basically the multiples of or perhaps corresponding angles with this specific aspect of divisions of 360 degrees. And we're going to see how we can identify the various range of course, the cosine and the sine of these specific angles which are going to be assisting us. Now, the De Moivre's theorem is one of the applications of complex numbers, which we have decided that we can represent in terms of this phasor of z given in terms of the x and of course the imaginary units and y given as such. And we had basically stated that in one of our videos on the concept of multiplication and division of complex numbers, we can have this one represented in terms of the cosine function and the sine function given as such. And we said that this basically are going to be assisting us in trying to represent these complex numbers in terms of polar forms. Now, in a sense, if we are going to, of course, do an analysis of these specific angles by finding either their roots and, of course, their powers, then we're going to do an application which is going to be assisting, requesting us or requiring us to have a knowledge of these specific ratios, which are going to be assisting us try to, of course, analyze De Moivre's theorem. Now, in this specific case, if we have these two particular angles for A and B, so I'm going to look at these angles in terms of set square angles and try to see how we are going to have a connection for the two functions, which, of course, as I've said, from the two basic trigonometric ratios and the concept of periodicity are going to be assisting us find the subsequent, of course, the sine and the cosine functions for the multiples of 360 degrees. Now, if I give this one as an angle A and B, now we can have this one given in terms of this specific representation. So this is going to be a right angle having 90 degrees and, of course, 45. So for the two base angles of 45 degrees, then therefore that implies that this specific side is congruent with that one. And if you look at this one, this is going to be having 90 degrees, and therefore the various, of course, edges are going to be different for B, of course, in contrast with the first one. Therefore, we're going to expect that from the Pythagoras theorem, if we are going to have this one as a 1 unit, this is going to be having a 1 unit as well. And if we try to, of course, analyze for the hypotenuse in this specific case, then this is going to be given in terms of the root over 2. So basically, it's going to be given in terms of the hypotenuse squared is equivalent to 1 squared plus 1 squared, which is equivalent to 2 given as such. And the h, of course, is going to be representing the root of 2 as per Pythagoras' theorem. So for the second case, we're going to see that if we have this one as a 1 unit, we can as well use a specific concept in trying to find the remaining other sections of this specific triangle. And we can do that one by an extrapolation of this specific section or a reflection in the base of this specific triangle, which can be, of course, illustrated as such. Perhaps I can just give it using this specific representation, whereby we're going to have this one as a reflection in the base of this specific triangle. And this is going to be forming particularly a range of angles which are going to be the same as the ones which we are going to have. So this is going to be congruent to this one, and this is going to be congruent to this other lower section. And therefore, if you try to look at this specific triangle, this is going to be a reflection of which we can, of course, give as an object and an image. So this is going to be a reflection along this specific line if we give it for this specific illustration in terms of course, x. And we are going to see that basically for this one, a reflection of this is going to be showing that the distance from this specific point to the apex of this angle or the apex of this specific figure is going to be forming 1 unit. And therefore, if these, of course, 3 sections are going to be the same for the stretch between here and the other 2 sections, this implies that this is going to be 1 unit as well, and therefore we are going to have this particular, of course, other edges having a stretch of 2. And if using Pythagoras theorem, then therefore we can find the base of this one as the square of 2, of course, minus the square of 1 given as such. And this is going to be 4 minus 1, which is equivalent to the root over 3 for the base of this specific triangle given as such. So this is going to be forming the root of 3. So therefore, for us to define other ratios for the trigonometric ratios of perhaps the sine, the cosine, and tan of different angles, we're going to have a range of values which we are going to obtain, especially if we consider these specific angles which we have given in terms of the set square angles of 45 and, of course, 30 and 60. So I'm going to give a particular table which is going to be assisting us try to define the various range of angles which we can define using the figures which I've just given on the board. So from our previous representation of the concept of these 3 basic functions for the sine, cosine, and the tan of theta, we can have this a particular acronym which we have been using for SOHCAHTOA, and we're going to define the various range of ratios for the sine, cosine, and of course the tangent of the various angles which you have given as set angles. And these are going to be defined by angles of 45 degrees, 30 degrees for this specific angle for the object. And of course, we're going to just to assume the image. And of course, we're going to see that for 45, 30, and 60 degrees, we can define the sine of those specific angles, cosine, the tangent, and of course, the sine for 30 degrees and the tangent given as such, and the 60 degrees. So in a sense, we are going to see that we're going to come up with the various ratios which are going to be defined using those specific angles. Now, this specific application is going to be assisting us try to define solutions to simple equations which are going to be involving the multiples of 360 degrees. And then, of course, since I'm going to be looking at some of the simple equations which we can define using the various range of angles. So kindly confirm from these various ratios which I've just given on the board in case you find a different ratio from this specific representation. Therefore, you can notify me in the comment section so that we can basically do an appropriate representation for that specific ratio. So in a sense, we can define various range of simple solutions which are going to be applied for the solutions of the concepts of an angle together with a multiple of maybe 360 degrees, which I said are going to be applicable for this specific aspect of the de Moivre's theorem. Now, if we have these particular angles which can be defined in terms of the sine of x, x is an angle which we can give in terms of the sine of x. So if this specific, the sine, so let's have this one as a sine over x is equivalent to the sine over y, then there's a relationship between this specific angle of x and y such that we can define this concept of x in terms of alpha. So this is going to be the sine over x is equivalent to the sine over alpha. Now the relationship between x and alpha can be given by giving it as alpha is equivalent to, or the x is equivalent to alpha plus 360 degrees n, or 360 n degrees. So in this case, n is going to be constituting a range of what we refer to as integers. Now this is going to be forming a central part of our, of course, discussion, which is going to be assisting us try to define de Moivre's theorem. This one can be given in terms of 180 degrees minus this particular angle of alpha. And of course, this is going to be given as plus 360 n degrees given as such. So in case we come across these two specific representation whereby n is a set of numbers which are going to be forming integers, this is going to be forming a basis for us in trying to find various ratios just as I've just given from the two particular angles of A and B, or a representation for A and B which I've just defined on the board. So in case we have a cosine function which can be given in terms of the cosine over x, so this can have a relationship with another angle alpha which can be given as alpha, whereby x is equivalent to either positive or negative alpha, and then we're going to have that specific angle over 360 degrees as a multiple given as such. So I've said this n is going to be forming a set of integers, and that is going to be forming our second ratio for the cosine. Now we can as well have this particular representation for the tan of x given in terms of the tan of another angle alpha. So the relationship between x and alpha can be given in terms of this particular representation, whereby we're going to have alpha plus 180 degrees. And in this case, this is going to be also having a multiple of n as I just mentioned. So for the last, for the three representations which I've just mentioned, we're going to see that n is going to constitute a range of course, these specific integers, and that's going to be forming the particular relationship which I wanted us to know from the, of course, small divisions for angles, which are going to be a set of square angles, and the concept of periodicity for the sine and the cosine function. Now, in our discussion on the concept of de Moivre's theorem and its application in finding powers and, of course, roots, then that's going to be a more comprehensive. Now, in this case, I'd like to invite our members to be checking our description boxes for various links of other videos. They're going to contain videos under for topics under a similar discussion, and of course assist us in trying to understand a wide range of topics which are going to be borrowing from one another. So that is it for now, guys. By God, please. We'll catch us in our next video.